very much.
Thank you.
So I'll quickly start out with this presentation and give a little bit of an intro why it is possible that Chromatic 3D Materials prints parts that are usable as flexible elastomer parts. That's kind of the trick here. And I'll give this around in the audience if somebody would like to catch it. Looks like you want to catch it, right? Why this is possible, and that is made possible because when we looked at the flexible 3D printing market, we first and foremost thought, okay, if you want to have something flexible, you need to cross-link it chemically in the part that you're printing, because any vulcanization process that creates a flexible rubber material will have that cross-linking when it is in the part. That's the reason you can't recycle a car tire, right? Because you can't remill it and make a new tire out of it. It is because of that process. There's a little video of how we print. You see here the print tip. A liquid comes out, and it chemically reacts without any light or without any heat except for the room temperature into this form. And the important thing about this is that with this technology, we can actually achieve the tensile strength to be roughly the same, and with roughly I mean plus minus 10 to 15% the same in all three room directions. And if you're providing seals, gaskets that have loads of higher pressure, of air pressure, or the bellows that have flexible loads all over the place, specifically in the z-axis, this is an incredibly important thing to realize. Now, when we print these little boxes, we have the bottom of the box, that's the XY flat. You see tensile strength of roughly 2,500, 2,800 psi. If you are looking at a Shore 90 polyurethane material, this is exactly the range you would expect this material to be. So if you're an engineer and you design your parts, right, you know, all right, I'm using a polyurethane, it's a Shore 90 material, or an EPDM, it's a Shore 90 material, and you would need to, in order to design the same part with the same geometry for the same function, you need the same material properties. And that was the thing that was realized using this printing technology that is very difficult to achieve for flexible part with melting something up and letting it cool down in order to create the part, or with using other types of cross-linking chemistry. Light-activated chemistry cannot give you those material properties. Another thing that was important specifically for the applications we're going to talk about next is that the materials are also flame resistant. For a traditional manufactured polymer, where you have your polymer backbone and you want to have the powder in there that makes the material flame resistant, you're introducing a powder into a long chain length, and that means that you have going to create slip that happens. So your material properties are going to degrade if you're in the post-processing add a flame retardant to a classic manufactured material. Now, since we do the cross-linking within the part, we actually build our cross-linked network around those particles. They're in the material, and they do not affect the material performance of those parts. Again, it is because of the chemical reaction happening in place of that. So we passed the flame retardancy tests for the materials that were shown here later, and for the bellow that disappeared already. And for the highest class, it did not disappear, very good. For the highest class in all rail applications. Now I can talk a lot about how durable these materials are. We can also show that on this tractor here. These pads are made using 3D printing, and if you see that the chains, when he goes around the corner, it rotates over 3 pads, 1.5 tons of equipment. That's how heavy this thing is. Rotates over just 3 pads, where since it's a chain drive, one is standing and you rotate this whole machine over that. And the shear axis that he's going over, that's the z-axis of the material. So that's the print height axis. We've not seen anybody else who was capable of producing a material that can survive these harsh use cases. And that's where you take over.
Yeah, thank you. Just let me just introduce myself. My name is Sebastian Otto. I'm head of additive manufacturing at Austrian Federal Railway. We do 3D printing for about 6 or 7 years now, and in the last 4 years we nearly made up to 400 use cases and managed to solve problems with additive manufacturing. This is not only about obsolescence. Most of the parts are obsolete, but also we do some systematic analysis where we search for potential in our ERP system, and one of the potential we found were elastomer parts, because we have lots of elastomer parts in our trains, like seals, grommets, bellows, membranes, and buffers. And the problem is to store them. You can't store them very long, and also we don't need a big amount of spare parts. So we don't use thousands of bellows. For example, of this bellow you already had in your hands, we only need 2 of them in a year. So it was important for us that we do with additive manufacturing. We managed to produce something like this. So the first use case I brought to you is some standard cable grommet, and what's the function of a cable grommet? You always you know to hold the cable, and the problem here, of course, you see the forecast. We only use 5 pieces per year. It's built in underneath here to hold the brake cables, and there is no other technology we could produce this in an economical way. So we were searching for a partner doing this flexible parts, and we found with Chromatic a good partner that they had this very interesting material. I think the first and the most challenging one was this one. I brought it to you. It's a dust cover for a leveling valve, from our trains, from our city jet, and again, only a little amount of pieces per year. But we didn't manage to find such soft material. So, for example, if you see, this is such a soft material, I have to put it on this valve. And we couldn't make it out of TPU. The third use case I brought to you, as I mentioned, this was the. Yeah, I think this was the first one we did together, because we failed doing this bellow out of other materials. Of course, we tried TPU, but TPU is we couldn't manage to do this in this softness, and we were trying to search for a solution, and of course. What we were most curious about was the flame retardancy. Bart already mentioned it. We have the problem in our trains that we always have to look about flame retardancy. So most of the flexible parts on the market, they don't have a certificate for flame retardancy. And with this technology, you can add some flame retardancy additives very easily and fulfill this certificates. And this is, I think, a game changer for the railway, because we can do now flexible part like this. They are not only with better mechanical properties, but also fulfills our highest flame retardancy standards. And therefore, I'm happy to have this partner and this material that we can build in our trains. Yeah. So this where only 3 of the use cases, of course, I mentioned in the beginning, we found over 200 potential use cases for this technology or for this material, and we are not alone. Also, the other railway companies from the other countries in Europe have the same standard that they have to fulfill, and they are also very curious about this technology. So, if you have some questions, then don't hesitate to ask us, and we will hopefully answer it.
All right. Does anybody have a question? No questions? There's one, all right. Breaking the silence.
Maybe I'll hand the mic to you.
All right.
José Carlos da Silva, Ninja Tech.
Yeah.
Are your flame retardant fillers able to linked to any polymer?
So we're not the maker of the flame retardants. We are the maker of the polyurethane resins that go in there. What we do is we just adapt. The polyurethane is used all over the place, like your mattress foam, seat cushions and trains, whatever. This is very often polyurethane. And there's existing materials that have been qualified for the exact same raw materials that we're using in our resin. And so with this technology, we don't have to do any fancy chemistry, right? We go to Ludwigshafen here across the Rhine. They have the flame retardants that we need, and they've been using those for 50 years. So this is how we are trying to solve these problems. As I always call it cheating, because really we're not inventing new chemistry, right? We're not making anything really complex. Our 3D printer is an XYZ framework that is very simple because it has just to do room temperature movements, right? There is no complex mechanics in there. And similar with the chemistry, we go out to the suppliers. That's why we choose these systems to start out with, these reactive systems, because every construction foam that you use to insulate a window will have the same chemicals in that we have in here, which also makes the business cases very interesting for the rail companies, because we don't start out with fancy molecules that cost thousands of dollars per kilogram. But we start out with the raw material for a mattress foam. And if you go to IKEA and look how much a mattress costs per kilogram, you can estimate how much you can get a good price on these parts.
I think not only railway.
Pardon?
Not only railway.
And we're not only working for railway, so there is more applications than just trains that are possible.
Planes should always not stay in flames, or cars. Yeah.
As well as, so since we have a few minutes. Like I was talking about the example of construction foam. Like, you know that if you ever worked with this stuff sticks to roughly everything. So with the technology, not only can you build these parts freely, but if you need a part that has a metal inlay, like a feather ring, or if you want to print on fabric to create a very fancy dress that lights up when you walk by the way, that's at our booth, then this is also possible with the technology, because it's got this flexibility to be used wherever polyurethane is used today. Your shoe soles, pretty much 95% of the people here have polyurethane shoe soles. Why? Because it's a great flexible material with a long lifetime. And that's one of the reasons this was chosen when we started out with Chromatic.
If anybody else has a question, I can bring the microphone. Or where can sorry.
Thank you. Do you hear me? Yes. Okay.
Yes.
I think you know Claire-Bremse.
Yes.
Railway brake system manufacturer. I come from Claire-Bremse, France, and just a question about the bellows. Have you tested the fatigue resistance, endurance resistance?
The pardon?
Can you talk
A little louder.
Have you tested the fatigue resistance?
Yeah, for these types of bellows, we've
Yeah.
tested fatigue tests just in this direction, but also the rotating, like as an access boot for a automotive manufacturer. We have done 200,000 kilometers in a test stand for rotational stability. and 600,000 cycles like that, compressing for 20 and expanding for 5%, which is the maximum use for these types of bellows. We do have data for hydraulic oil, grease, gasoline stability for different materials. We do actually have specific material grades for specific chemical stability, because you can't, like in the Shore A50, we have 4 different grades covering 4 different chemical resistances, and that goes from Shore A50 to Shore D65, roughly every 5 units on the scale. We can change the hardness, so if you need something that is 85, 90, 75, that would all be available in the different hardnesses, as well as in different material properties.
Okay, thank you.
Anybody else? Where in the hall can we go to play with these parts?
12.1 E110.
12.1 E110.
Yeah.
Okay.
Yeah.
Perfect. Thank you very much, gentlemen, for your presentation.
Thank you.
Thank you.